This is the story of a dream, perhaps one of humanity's oldest and most audacious. The dream of a thinking machine. It's a tale that begins not with silicon and code, but with myths of bronze giants and legends of clay golems. We'll journey from the smoke-filled parlors of Victorian England, where the first computers were imagined, to a pivotal summer conference in 1956, where a handful of brilliant tweed-clad optimists officially christened a new field: artificial intelligence. But this is no simple tale of progress. It's a story of dizzying highs and crushing lows, of a dream that was promised then deferred, left to freeze in the long AI winter. We'll uncover how it survived in obscurity, fueled by niche expert systems and a quiet, stubborn belief in its potential. Then we'll witness its spectacular rebirth, a renaissance powered by two unlikely forces: the explosion of the internet and the graphical demands of video games. This is the story of deep learning, of machines that could finally see, and of the revolution that followed. We'll arrive in our present moment, a strange new world where we converse daily with large language models, our new, slightly unhinged and endlessly fascinating artificial companions. This isn't just a history of technology, it's the biography of an idea, and a look at how it's finally, complicatedly, come of age. I'm Danny, and this is a new episode from both our theme for this week, Living in the Age of AI, and from our series, The Human Odyssey. Let's begin with a confession. You and I, we're already cyborgs. Not in the chrome and laser eyeball sense, but in a way that's far more intimate and, frankly, a lot more mundane. The thought you were trying to complete just now, it was probably nudged along by a predictive text algorithm. The song that will lift your spirits this afternoon was likely chosen by a recommendation engine that knows your emotional state better than your spouse. The quickest route to that new coffee shop, the one you found through a search engine that sifted through 1 trillion data points in a fraction of a second, was charted by a ghost in the machine. We live our lives seamlessly integrated with an invisible intelligence, a vast distributed network of artificial minds that filter, sort, predict, and present our reality to us. And most of the time, we don't even notice. We've become so accustomed to these cognitive prosthetics that we treat them like air. But this intelligence, this thing, didn't just appear. It wasn't beamed down from space or conjured in a single eureka moment in some sterile Silicon Valley lab. No, the story of artificial intelligence is the biography of a dream. It's an ancient, stubborn, almost primal human yearning. It's a multi-generational epic filled with brilliant protagonists, tragic setbacks, moments of unbelievable hubris, and a plot twist so elegant it would make a novelist weep. It's a story that begins long, long before the word computer even existed. So let's start with Act 1, The Ancient Whispers and Clockwork Hearts. Before we could build the thinking machine, we had to imagine it. And oh, how we imagined it. The dream's first stirrings aren't found in technical manuals, but in mythology and folklore. The ancient Greeks told tales of Hephaestus, the god of invention, who forged magnificent automatons to serve him in his workshop. His most famous creation was Talos, a colossal man of bronze who circled the island of Crete 3 times a day, hurling boulders at invading ships. Talos wasn't a statue, he was a guardian, an autonomous entity with a single divine purpose. Jump forward a couple of millennia to medieval Prague, and you'll hear the legend of the golem. In this tale, a rabbi forms a man from river clay and animates him by placing a slip of paper with a sacred name, Hashem, in his mouth. The golem was a protector, a tireless worker, but also a cautionary tale, a powerful, unthinking servant that could and eventually did run amok. Talos and the golem are the primitive source code for the AI dream. They embody our twin desires: the craving for a powerful, intelligent servant to ease our burdens, and the deep-seated fear of what might happen if that servant ever slipped its leash. For centuries, this dream remained locked in the realm of myth and magic. But then, during the Enlightenment, something shifted. The universe, once seen as the capricious playground of gods, was reconceived as a grand, intricate clock. If the cosmos operated on logical, mechanical principles, then why not life? Why not thought itself? Philosophers and mathematicians began to lay the conceptual railroad tracks that would one day carry the AI train. In the 17th century, Gottfried Wilhelm Leibniz, a man of terrifying intellect, dreamed of a universal language of thought, an algebra of concepts where all human arguments could be settled by simple calculation. He imagined a machine that could reason. "Let us calculate," he declared, would be the only response needed to resolve any dispute. He never built it, but he planted a flag on a critical piece of intellectual territory: the idea that thought could be mechanized. That idea festered for another 150 years until it found its champion in a fantastically grumpy, brilliant, and perpetually ahead of his time Englishman named Charles Babbage. In the 1830s, amidst the soot and steam of industrial London, Babbage designed his analytical engine. This sprawling brass and iron behemoth, powered by a steam engine, was, for all intents and purposes, the first general-purpose computer ever conceived. It had a mill, the CPU, and a store, the memory, and could be programmed using punched cards, an idea borrowed from the jacquard loom that wove complex patterns into fabric. But Babbage, the hardware guy, had an indispensable partner in the software visionary Ada Lovelace. The daughter of the poet Lord Byron, Lovelace possessed a mind that saw beyond the mere crunching of numbers. She looked at the analytical engine and didn't just see a calculator. She saw a machine that could manipulate any symbol, not just digits. She realized it could, in theory, compose music, create art, or perform any task that could be expressed as a logical sequence. In her notes, she wrote what is now considered the world's first computer program. But she also issued a profound and prescient warning. The analytical engine, she wrote, has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. The dream now had a body, at least on paper. It had a potential brain, but Lovelace's caveat hung in the air. It was an obedient brain, not a creative one. The spark of genuine intelligence was still missing. And that brings us to Act 2 of our story, the birth and the unbridled optimism. The 20th century arrived, and with it, war, chaos, and a frantic acceleration of technology. The dream of the thinking machine, once a parlor room curiosity, was about to become a strategic necessity. And its next great prophet was a man as tragic as he was brilliant: Alan Turing. During World War II, Turing was instrumental in breaking the German Enigma code, a feat that arguably shortened the war by years and saved millions of lives. He did it by building an electromechanical machine, the bomb, that could think through permutations faster than any human. He had seen firsthand how a machine could perform a task that was, in essence, a form of intelligence. After the war, Turing wasn't done. He turned his gaze from code breaking to the very nature of thought itself. In a 1950 paper, he sidestepped the sticky philosophical question of "can machines think?" and replaced it with a practical, elegant proposal: the imitation game, now famously known as the Turing test. The setup is simple. A human interrogator types questions to two unseen entities, one a human, the other a machine. If the interrogator cannot reliably tell which is which, the machine is said to have passed the test. It's a pragmatic behavioral definition of intelligence. If it talks like a human and reasons like a human, who are we to say it isn't thinking? At the same time, other researchers were trying to build the machine's brain from the ground up. In 1943, neurophysiologist Warren McCulloch and logician Walter Pitts proposed the first mathematical model of a biological neuron. Their threshold logic unit was a radical simplification, of course, but it captured a fundamental essence. A neuron receives signals, and if those signals reach a certain threshold, it fires and sends a signal of its own. By linking these artificial neurons together, one could, in theory, create a network that could learn and compute. It was the first faint blueprint of a neural network, a digital echo of the brain's wetware. The pieces were all there: the theory of computation, the idea of an imitation game, the model of an artificial neuron. All that was needed was a spark to bring them together, a moment to give the dream a name and a mission. The moment came in the summer of 1956. A handful of the brightest minds in computation and logic gathered for a 2-month workshop at Dartmouth College. It was an all-star team. John McCarthy, who coined the very term artificial intelligence for the conference proposal, Marvin Minsky, a young genius exploring computational models of the mind, Claude Shannon, the father of information theory. They were brilliant, they were ambitious, and, let's be honest, they were breathtakingly optimistic. Their proposal for the workshop declared their intention to make a significant advance in creating thinking machines, stating that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to stimulate it. They believed that in a single summer, they could lay the groundwork for solving language, abstraction, and creativity. They were, in a very real sense, the founding fathers of a new field, drafting its Declaration of Independence. They believed the birth of a true thinking machine was not a matter of if, but when. And they thought when was maybe a decade or two away. Obviously, they were wrong, spectacularly, painfully, and wonderfully wrong. That brings me to Act 3 of our story, The Long, Cold Winter. The initial years after Dartmouth were a heady time. Programs were written that could solve algebra word problems, prove geometric theorems, and play a decent game of checkers. Researchers, fueled by government funding, largely from the military who were very interested in things like automated translation and photo analysis, made grand pronouncements. In 1965, one of the pioneers, Herbert A. Simon, predicted that machines will be capable within 20 years of doing any work a man can do. The problem was, they were tackling the intellectual equivalent of Mount Everest with the gear of a weekend hiker. They quickly discovered a few inconvenient truths. First, the curse of dimensionality. The number of possibilities in even seemingly simple problems explodes exponentially. To make a chess program that could look ahead just a few moves required staggering amounts of computation. They were trying to boil the ocean with a teacup. Second, the problem of common sense. They could program a machine with the rules of logic, but how do you program it to know that water is wet? Or that if you let go of a glass, it will fall and break? The world is filled with an unthinkably vast amount of implicit, unspoken knowledge that we humans navigate effortlessly. For a machine starting from scratch, it was an impassable wall. A computer could be a logical genius, but a common-sense idiot. By the mid-1970s, the initial exuberance had curdled into disappointment. Government agencies like the US's DARPA and their UK counterparts looked at the lack of progress on the grand promises and decided to pull the plug. Funding dried up, labs were dismantled. The dream, once the toast of the scientific community, was suddenly an embarrassment. This was the beginning of the first AI winter. The dream didn't die, though. It just went into hibernation, surviving in a few less glamorous forms. The most successful of these was the expert system. The idea was simple. If we can't build a general intelligence, let's build a highly specialized one. Researchers would interview a human expert in a narrow domain, say diagnosing blood infections or identifying promising sites for mineral exploration, and painstakingly codify their knowledge into a massive set of if-then rules. Expert systems like Mycin for medicine or Prospector for geology were actually quite successful and commercially viable. They were the first truly useful AI applications. But they were so brittle. They had no real understanding, just a giant rulebook. Ask them a question slightly outside their domain and they would break completely. They were like a digital brain in a box that only knew about one thing. Still, they kept the flame of AI alive through the long, cold winter of the 1980s. And that brings me to Act 4 of our story, the data renaissance and the unlikely savior. As the 20th century drew to a close, the dream of a true learning machine, the kind of brain-inspired network McCulloch and Pitts had first sketched out, was still largely on the fringes. Those neural networks were seen as interesting but impractical. They were computationally expensive and required vast amounts of data to train, neither of which were readily available. And then, two seemingly unrelated things happened that would change everything. First, the World Wide Web exploded. Suddenly, humanity was engaged in a massive, unprecedented project, digitizing itself. Our conversations, our photos, our shopping habits, our encyclopedias, our cat videos, it was all being converted into data. For the first time in history, there was a planetary-scale dataset, a feast for any learning algorithm that could be built to consume it. Second, video games got really, really good. To render the increasingly realistic 3D worlds of games like Quake and Unreal, hardware companies developed specialized processors called graphic processing units, or GPUs. GPUs were designed to do one thing exceptionally well: perform thousands of relatively simple calculations in parallel. This was perfect for rendering pixels on a screen. It took a while for anyone to realize it, but it turned out that the math for rendering graphics was remarkably similar to the math required to train a neural network. A GPU, in essence, was a perfect, ready-made brain-building machine. The dream now had two things it had desperately lacked for 50 years: an infinite supply of food, the data, and a powerful new engine to digest it, the GPUs. The stage was set for a revolution. The prophet of this new age was a researcher named Geoffrey Hinton, who, along with his students, had stubbornly kept the faith in neural networks through the winter years. They refined the algorithms, figuring out how to build deep networks with many layers of artificial neurons, allowing them to learn far more complex patterns. The thunderclap moment came in 2012. It was a competition called the ImageNet Large-Scale Visual Recognition Challenge. The task? Build a program that could correctly identify objects in a massive dataset of over 1 million images. For years, the best programs had hovered around a 25% error rate. In 2012, Hinton's team entered a deep neural network named AlexNet. It didn't just beat the competition, it annihilated it, achieving an error rate of just 15.3%. To the outside world, it might have sounded like a minor technical victory. To the AI community, it was the equivalent of the sound barrier being broken. A machine could finally, reliably see. The world of computing had just tilted on its axis. The AI winter was officially over. Spring had arrived. And that, of course, brings me to Act 5, the age of the giants and the new oracle. The years after AlexNet were a whirlwind. The techniques of deep learning were applied everywhere, with spectacular success. AI could now transcribe speech better than humans. It could detect cancer in medical scans. It drove the recommendation engines of Netflix and Amazon. In 2016, Google's AlphaGo, a deep learning system, defeated Lee Sedol, the world's greatest Go player. A feat considered a decade away, as Go is vastly more complex than chess. But all these systems were still, in a way, specialized. They were narrow AI. AlexNet could see cats, but it couldn't tell you a story about one. AlphaGo could master Go, but it couldn't order a pizza. The dream's final frontier was language, the messy, contextual, glorious stuff of human thought. The next great leap came with a new kind of neural network architecture introduced in a 2017 paper by Google researchers titled "Attention is All You Need." The architecture was called the transformer. Its key innovation was the attention mechanism, which allowed the model to weigh the importance of different words in a sentence, no matter how far apart they were. It could learn not just words, but context. It could learn the grammar of everything. This was the breakthrough that unlocked the large language model, or LLM. Companies like Google, Meta, and a small, audacious startup called OpenAI began training massive transformer models on, well, pretty much the entire internet. They fed these models trillions of words, letting them learn the patterns, relationships, and structures of human language and knowledge. The result is the strange, powerful, and often baffling world we live in now. We have chatbots like ChatGPT that can write poetry, debug code, explain quantum mechanics, and plan a vacation. They are our new oracles, our infinitely patient tutors, our creative partners, our tireless, slightly unhinged, and pathologically helpful interns. And so here we are, the dream of a thinking machine born in myth, sketched out on paper by a Victorian mathematician, given a name by a handful of optimists in 1956, left for dead in the 1970s, and resurrected by video games and the internet, is now a chat window on our screens. It is, of course, not the end of the story. We are still grappling with Ada Lovelace's 180-year-old question. Are these machines truly originating anything? Or are they just fantastically complex mimics, stochastic parrots just predicting the next most likely word? Have we created a mind? Or have we just built a mirror that reflects the entirety of our digital existence back at us, warts and all? The questions of consciousness, of ethics, of bias, of what this all means for our own identity are now no longer academic. They are urgent and real. The biography of this dream is still being written, and for the first time, we are not just its authors, but its co-stars. The next chapter is ours to write, together with the strange and wonderful thinking machines we finally, after millennia of dreaming, managed to create. And nobody, not even the smartest machine among us, knows how it's going to end. And with that, my friends, we come to the end of our story, the story of AI. I hope you enjoyed it. And with this episode, we conclude our theme for this week, living in the age of AI. Of course, that's not the end of the story. Nobody knows the end of the story. And there's a lot of room for talking and discussing these things. So you can do that on the website, because I've also included a lot of content on the website related to living in the age of AI. That being said, thank you very much for listening, and I'll see you again next week with a new theme. And don't forget that if you want to unlock access to all the content that I create, you can do that by subscribing on Apple Podcasts or on Patreon. Thank you very much for listening. I'll see you again next time. And remember, never stop learning with English Plus Podcast.